Yeah. So yeah. So as I said last time, we saw the definition of homogeneous coordinate ring and so on. So for a polynomial f is said to be homogeneous. A polynomial in n+1 variable is said to be homogeneous if each monomial of f has the same degree. Yeah, so something like this. And then we saw this lemma that you can characterize it by this property that f of lambda a0 to lambda an is same as lambda power df a0 to an for all lambda in the base field k and a0 to an in k+1, where d is the degree of this polynomial. So this is a characterization when k is a infinite field. Otherwise, you only have one direction if k is a finite field. Yeah. And we defined. We said an ideal I is said to be homogeneous if I is generated by homogeneous polynomials. Yeah. So homogeneous ideals are the object of study, and these corresponds to algebraic subsets in projective spaces. So another characterization of homogeneous ideal was that if f, a polynomial f belongs to I, then that need not be homogeneous, obviously, but if you decompose it in homogeneous pieces of various degrees, so homogeneous piece of degree 0, degree 1, and so on, then each of these homogeneous pieces should also belong to I, if I is a homogeneous ideal. And conversely, so if I is a homogeneous ideal, then this happens, and if this happens, then I is a homogeneous ideal. So it's a characterization. Then, as I said, algebraic subsets of Pn are given by zero sets of homogeneous polynomials, and x is equal, and we saw that this for a homogeneous polynomial, if it vanishes at some point p of Pn. So remember, Pn is same as an+1 modulo the equivalence relation. So it's lines in an+1. So it doesn't matter which point, which non-zero point of that line you take. Yeah, if f is homogeneous and it vanishes at some point of that line, then it will vanish at every point of that line because of this property that f of lambda a naught to lambda n is lambda power df of a naught to n. Yeah. So if f of a naught to n is 0, then f of lambda a naught to lambda n is also 0. Okay, so this makes sense. Fp is equals 0 is well defined. Yeah. And it does not depend upon the choice of representative of P. So this is denoted by Z P and S, if you like. I mean, if you want to so I'll not do that here. So maybe separately I'll. So sometimes if there is confusion whether which zero set we are talking about, we put this. Yeah. So we'll do that when we are trying to switch between an+1 and Pn and so on. We also saw that if I is a homogeneous ideal, then Zi. Oh, sorry. So we define Zi to be this guy. Yeah. If I is a homogeneous ideal, then Zi is defined to be those points of Pn such that Fp is 0 for all homogeneous F in I. Yeah. So this is how we get this is how we get the algebraic subset of corresponding to a homogeneous ideal of this thing. This was Z of S, and S was a collection of homogeneous polynomials. Yeah? So for homogeneous ideals, you don't take the zero set of every polynomial in I, because then Fp equals 0 may not make sense if F is not homogeneous. So you just take homogeneous polynomials. That's good enough. And then I just said this, that if I and j are homogeneous, then there's the ideal generated by I and j is also homogeneous by definition. And intersection of homogeneous ideals are also homogeneous by the other characterization, if you like. And hence, and we also have this identity Z. So this, even if you put, whether you put affine or projective, it holds. So affine we have already seen, and projective is the same proof. And if you are given a subset of P1, then you can define, so the notation, okay. I mean, I've been using interchangeably, so script I or just standard I. So I think in the earlier part I was using script I. So let's just stick to it. So sometimes it's just regular I, yeah. So ideal of X is those those homogeneous polynomials in the ring such that f of p is 0 for all p in X. So that is the ideal of definition of a subset of Pn. Yeah. So of course, and then you consider the ideal generated by these homogeneous polynomials. Yeah. So if you just take these homogeneous polynomials, it's obviously not going to be a ideal. So you have to take the ideal generated by these polynomials. Because if you take sum of two different degree ones, so f, if say f is such a polynomial, then of course f square is also such a polynomial. But f plus f square is not such a polynomial. It's not homogeneous. So you have to take ideal generated by them. Okay, so but by definition, Ix is a homogeneous ideal. Yeah, because you are taking the ideal generated by certain homogeneous polynomial. And then we gave the Zariski topology on Pn to be closed sets that to be such that the closed sets are algebraic subsets of X. Okay. And of algebraic subsets of Pn. And if you have some X which is an algebraic subset of Pn, and you then you give that X a subspace topology, let's say. Yeah. So for X, that and the closed subset of X will be algebraic subsets of Pn which are contained in X. Yeah. And note that like in the affine case, Z of I of X is I closer, is X closer. So if X is not really algebraic subset, if it is some arbitrary subset of Pn, and you take Z of I of X, then what you get is the closure in this topology, Zariski topology. Okay. So one has to check that this is indeed a topology. So, but that follows from this bullet essentially. With I intersection J, you have to. This holds not just for two ideals, but any number of ideals. Yeah. And the fact that empty set and whole of Pn are closed subsets, are algebraic subsets. Any questions so far? So this, so whatever I said so far was done last time. So now we'll see something new. So this was just recollecting what we did last time. Okay. So we also observed that the only maximal ideal in this homogeneous maxima, which is homogeneous in this coordinate ring, is x naught to xn. Yeah, the ideal generated by x naught and x to xn. So this ideal has a name. It is called irrelevant maximal ideal. That is because it doesn't play any role in the geometry. So note that Z, if you look at the zero set of X, this maximal ideal, you get the origin in an plus 1. Yeah. And origin does not correspond, so you have to remove the origin and then take the equivalence class. Yeah. So it doesn't correspond to any point in Pn. Yeah. So if you are trying to figure out what is the zero set of this irrelevant maximal ideal in Pn, you'll get empty set. Yeah. So you consider P such that f of P is 0 for all homogeneous polynomial in this, then you can't find any such P. Yeah. And so I think we discussed this as well. So for a point P in Pn, maybe for P1 we discussed this. So if you have A0 to An, a point in Pn, then the corresponding homogeneous ideal is given by this thing. Yeah, so maybe we'll argue this out. So is given by A0 x1 minus A1 x0, A0 x2 minus A2 x0, and so on, A0 xn minus An x0. So in fact, you can check that. So first observation is, I'm just here. It seems to give an impression that 0th coordinate is somewhat special, but note that this ideal generated by this contains ai xj minus aj xi. Yeah, you just subtract the ith term from the jth term in this list, then you'll get this expression. Yeah. So it contains all this thing, and the ideal generated by this, all this where I and j varies between 0 and n gives you this. Okay. So first thing we observe is that the ideal of P is this guy. Yeah. So so remember we also talked about cone. So if X is some algebraic subset of Pn, then we can look at the cone of P, cone over that algebraic set Cx, which is basically, you think of yeah. So you basically consider its pre-image in An plus 1. So Pn is a quotient of An plus 1 minus origin in, so you have a quotient map from An plus 1 minus origin to Pn. You just look at the pre-image and throw in the 0. So that is what the cone is. Yeah, you basically, for every point in X, you consider the whole line in An plus 1 passing through that point. Yeah. So we want to know the ideal of definition of P. So it's same as looking at the ideal of definition of the line passing through or through origin and this point A0 to An. You can choose any representative; it doesn't matter. That is the line. Yeah. So Cp, or in other words, Cp, the cone over this point P is given by the n plus 1 tuples lambda A0 to lambda An, where lambda is any arbitrary element of K. Yeah. So what is I of Cp? So of course, so we basically want to show that I of ideal of definition of this line is this guy. Yeah. So that's clear. Yeah, because first of all, A0 x1 minus A1 x0 up to An A0 xn minus An x0. They of course all these elements do belong to ideal of definition of Cp, because each of these polynomial vanish on Cp. Yeah, the cone of this point. Okay, because you just look at it. A0 x1 minus A1 x0 vanish at this lambda A0, lambda A1, lambda An, and so on. These just cancel out. And if you go mod this ideal, A0 x1 up to A. So this containment is okay. Now I just want to prove the equality. So note that if you go mod this ideal, you get K is isomorphic to Kx0 if A0 is non-zero. Yeah, because you can write x1 as A1 over A0 x0 and so on. Yeah, xn as An over A0 x0. And hence you can give a map from, so you'll send xi to ai over a0 x0, yeah, and the kernel is going to be precisely this ideal. Yeah, so you can show that this is isomorphic to kx0 if a0 is non-zero. If a0 happens to be 0, then you look for some so one of them has to be non-zero because it's a point in Pn. Yeah? So it's going to be, so the point is it's going, is isomorphic, if you go mod this, is going to be isomorphic to a polynomial ring in one variable, which is over a field, which is an integral domain. So that tells you that this this ideal which you are looking at in the right hand side is a prime ideal. Yeah? So this is a prime ideal. And of course, if you look at the vanishing locus of this guy, so I meant here, and the vanishing locus of this guy a0 x1 minus a1 x0 to a0 xn minus an x0 in an plus 1, if you like, then this is equal to exactly CP. Yeah. So so radical of this is going to be the ideal of definition of CP. But this is a prime ideal, so it is its own radical. So you get that ICP. Yeah. So we saw that, so what we concluded is that ideal of definition of P is precisely this, this homogeneous ideal. So in fact, we will see in a bit that IP is maximal among homogeneous ideals whose radical is properly contained in the irrelevant maximal ideal x0 to xn. Okay. So so this point corresponds to maximal. So points in Pn does not correspond to a maximal ideal in homogeneous maximal ideal in x0 to xn. Yeah. It does not correspond to maximal ideal in x0 to xn because most of the maximal ideals are not homogeneous. There's only one guy which is homogeneous. So, we can't expect a bijection between maximal ideals of x0 to xn and points of Pn. But there is a bijection between maximal ideals, maximal among certain other class of ideals, and points of Pn. Yeah, so maximal among such class of ideals. So maximal among homogeneous ideals whose radical is properly contained in the irrelevant ideal. And such ideals we call it homogeneous maximal ideal. Yeah, so maybe I can underline it with that. So I maximal elements of this collection, homogeneous ideals J of K x0 to xn such that radical of J is properly contained in x0 to xn. So it's important to put radical because you can take a square of this irrelevant maximal ideal. Yeah. And zero set of the square of irrelevant maximal ideal is also going to be the origin, and it won't correspond to any point in the projective space. Yeah. So we should take this. Okay, so we will see this fact also. We will see that that maximal homogeneous maximal ideal. So so these are called homogeneous maximal, yeah, not maximal ideals, but homogeneous maximal. So you see that homogeneous maximal ideals of K x0 to xn corresponds to points in Pn. Okay. So maybe so that's like Hilbert Nullstellensatz. That's also so maybe a projective version of Hilbert Nullstellensatz. So it follows from the usual Hilbert Nullstellensatz because there is relation between. So you just pass to the cone. So we'll do that in a bit. So maybe we'll do this Hilbert Nullstellensatz. Are there any questions? Maybe I'm going too fast. So are there any questions before I continue? Okay. So I hope everything is making sense. So Hilbert Nullstellensatz. So remember, ideal of definition of z of I for is equal to radical I. This statement is true for in the affine setup, and this is true even in the projective setup. Yeah. So remember, z of Pn of I means those points of the projective space such that every homogeneous element of I vanishes at that point. Yeah. And ideal of definition means those homogeneous polynomials which vanish at every point in Z Pn of I. Yeah. And then you take the ideal generated by that. Okay, so that should be same as radical of I. If radical of I is properly contained in x naught to xn. Because when otherwise there is some problem, yeah. So the problem is captured in point 2. So z of Pn of I is empty in two circumstances. Either radical of I is x naught to xn. Yeah. So if radical of I is x naught to xn, then we know that z of radical of I is going to be the origin, and hence it's the corresponding. So in Pn it will lead to empty set. Or even if one belongs to I, so if I is, so of course if I is the whole ring, then also I is a homogeneous ideal. Yeah, and then also we get that Zi is empty. Okay, so that's why we to get this this thing on the nose, we insist that radical of I is properly contained in x naught to xn. Okay. I guess we can, even if we assume that I is different from kx naught to xn, then also this should ideal. Yeah, so then one has to take the convention that yeah, then I don't know, I of empty set, one has to figure out what the convention is in the projective setup. Okay. So so one should take the whole ring. Yeah, so it's better to have this. Okay, so first we'll do this lemmas. This I is homogeneous, then radical of I. So we will argue this. So this is not difficult. I mean, nothing in this section is going to be difficult. So first I is homogeneous ideal, then its radical is also homogeneous. That's what we want to argue. Yeah. So suppose I is homogeneous and F is F belongs to radical of I. Yeah. Then F you can write it as sum of various homogeneous pieces. Yeah. And I'm just going to list down those degrees for which the homogeneous pieces are non-zero. Yeah, so Fi1, Fi2, Fid, where I1 is strictly less than I2 is strictly less than I2. Yeah, I mean you can list down all of them, but doesn't matter. Let's just list down only those which are for which is non-zero. Okay. Now F belongs to radical I means F power n belongs to I for some n. Yeah. Maybe this n and that n, I don't want to confuse, so maybe I'll put m. Yeah, so no, projective space is also Pn. Yeah. So for some m, f power m belongs to I. And if you raise it to the mth power f, this right-hand side of this expression for f here, then what you get is that you'll get fi1 power m plus some higher degree terms, because I2 has higher degree, I3 has higher degree, and the mixed terms will also have degree higher than I1 power m, I1 times m. Yeah. So this is f power m belongs to I, and f power m is same as f I1 power m plus some higher degree terms, and that belongs to I. And since I is homogeneous, and I1 power m is also, so I1 is a homogeneous polynomial, and mth power of a homogeneous polynomial is also homogeneous. So this is a homogeneous piece of this this polynomial contained in I. Yeah. In fact, degree I1m homogeneous piece of this polynomial. So that tells you that f I1 power m belongs to I, because that was one of the characterization of homogeneous polynomial. So we are using the characterization. So what we'll show is that fi1, fi2, etc. belong to radical I. So we already got that f I1 power m belongs to I. So we got f I1 belongs to radical I. Okay. So once you have fi1 belongs to radical I, then the sum, then you can subtract that from f, and you get fi2 plus so on fid belongs to radical I, and then you apply the same algorithm to show fi2 belongs to radical I, and continue this way to show that fij belongs to radical I for all. Okay, yeah, and that proves that the radical I is homogeneous. Okay. So what we have shown is that I is homogeneous implies its radical is homogeneous. Okay. So remember, so in particular, what it says is that so if I is a homogeneous guy, then it's you look at V of I in the zero set of I in an plus 1, then you get a cone. Yeah. And if you look at the ideal of definition of that cone, you get the radical of I. Yeah. So what it says is that ideal of definition of a cone is going to be a homogeneous ideal. Yeah. Because any cone, again, you can write it as a zero set of some homogeneous ideals. Yeah. So that is the idea which will be sort of. So that is how one should interpret using. So that is how we connect between projective algebraic subset in projective space and affine space, and try to sort of get this bijection between ideas and zero sets. Okay, so let's see the proof of this this theorem, that ideal of this is same as the radical ideal. So note that in the radical of I is same as ideal of definition of z of an plus 1 I in an plus 1. So if you are looking at the affine setup, this we know, and that was the Hilbert Nullstellensatz. Yeah, so one direction was okay, which is radical I is contained in this guy was okay, but for the other direction you used Hilbert Nullstellensatz. So that we know. We only, so it's enough to show this this equality. Yeah. So if we show this equality, or containment, both sides containment, then we are good. So let's just argue both containment. So suppose, so what is the definition of, so let's say f belongs to the right hand side. Yeah. So what does that mean? So that means f is homogeneous and fp is 0 for all p in zpn of I. Yeah. So that tells you that f twiddle is 0 for all a in zan plus 1 I. Yeah, because Zpn of I is projective points, but that corresponds. So you just look at the cone corresponding to that. Yeah. So that's same as f a tilde is 0 for all a tilde in Zan plus 1. Yeah. So that tells you that f has to, since f vanishes at everything in Zan plus 1, then of course f belongs to IAN plus 1. Ideal of definition of AN plus 1 Zan plus 1 I, which is same as radical I. Yeah. So we have this this containment, which is same as radical I by Hilbert constants. So we have this containment, and for the other containment, so we take something. So what we want to do is show that if f belongs to radical I, then it's contained in the right hand side. So that's the easier step that I don't think require Hilbert Nullstellensatz. So let's take f homogeneous and f belongs to radical I. Then some power of f belongs to I by definition. So since some power of f belongs to I, that power of f vanishes at all points. So fp is going to be 0 for all points in Zpni. Yeah, by definition of Zpni. Zpni, remember, is a set of all points where every homogeneous polynomial of I vanishes. Yeah. So technically, it's f power mp equals 0 for all p. But if f power mp equals 0 for all p, then fp also equals 0. So maybe one should do here f power mp equals 0 for all p in Zpni. But I mean, we are talking about a field, yeah. So if f power m vanishes, then f also vanishes. So then f of course belongs to the ideal of definition. So f is homogeneous and it vanishes at all points of Zpni. So f belongs to the ideal of definition of Zpni in this thing, yeah, because the ideal of definition in Pn of Zpni is ideal generated by all homogeneous polynomials which vanish on this thing. So f is homogeneous and it vanishes on this, so it actually belongs there. Yeah. So that tells you that radical of I is, so you get the other. Yeah, so what you get is that so what did we see? We see that every homogeneous element of radical I is contained in this guy, but radical I is homogeneous ideal. So it is generated by all the homogeneous polynomials, homogeneous elements in I. So we get that radical I is contained in this. So we didn't see this, so this step doesn't show every element in radical I is there, but we showed only homogeneous elements of radical I. But since radical I is homogeneous ideal, and the right hand side is also homogeneous ideal. This is also homogeneous. So that tells you that the whole of radical I is contained in there. Or maybe it's not required. This is an ideal is good enough. Radical I is homogeneous means it's generated by all the homogeneous elements, and that's it. Okay. So that completes the proof of the Hilbert Nullstellensatz. So the essence of the proof, I mean, the difficult part is embedded here. The difficult part is in the Hilbert Nullstellensatz for the affine setup. The rest is just working through what is, I mean, just chasing this through. Yeah. So maybe I'll make a remark. So no, which I was trying to do. So remark. So the point is. um, if X is in Pn, then Cx, its cone in En plus 1, is some algebraic subset. Yeah, if X is algebraic subset of Pn, then its cone is some algebraic subset of En plus 1. And ideal of so if you look at the ideal of definition of the cone of X, this is say in the affine setup. So meaning this is saying that all polynomials which vanish on cone of X, all polynomial in Kx not to Xn plus 1 which vanish at cone of X. This is same as ideal of definition of Pn of X. So here this is the ideal generated by all homogeneous polynomial which vanishes at every point of X. Yeah? So what we have observed is that these two happens to be same. Okay. So the statement saying the radical of a homogeneous ideal is as a homogeneous ideal is same as saying that ideal of definition of any cone is cone in En plus 1 is homogeneous ideal. Okay. So I hope this is sort of clear. And also note that any cone, if you take any cone in En plus 1, so by cone I mean that if a point belongs there, point in En plus 1 is there, then the whole line passing through that point and origin is there. So maybe, so if y contained in En plus 1 is a cone, then y is given by some homogeneous ideal. Yeah. So y, so which homogeneous ideal y will be given by? So how do you show y is given by a homogeneous ideal? So you take any point on y different from origin. Yeah. Then of course the whole line is there. So I don't know. So maybe you can write it as intersection of I of ideal of P, where P belongs to Pn, belongs to, sorry, y minus origin modulo the equivalence class. Yeah, so maybe yeah. So yeah, this is right. So I want to really think of it this way. So this is same as intersection cone of a point. P will for P in yes. So maybe this is the second one is more right. Yeah. And this is also okay. So P in Y. IAN plus 1 of CP. So here we are thinking this ideal of definition in the affine setup. In the second one, in the first one, we are thinking ideal of definition in the projective setup. Yeah. So why? So as we know, intersection of homogeneous ideals are homogeneous. So so if you take zero set of this guy, you'll get Y. That's the one I want to see. Okay. Okay, and in fact, so by what we argued, that tells you that in particular I of Y is homogeneous ideal. Okay, so maybe I've overdone this this, but the correspondence is you look at homogeneous ideals in kx naught to xn, and in the geometry side you look at cones in en plus 1, yeah, and then mod out by the equivalence to get subsets in Pn. The equivalence fields only for two kinds of ideals, which was mentioned here. So maybe part 2 is still to be done. Yeah. So this only proves part 1. So maybe part 2, but maybe part 2 is clear. Yeah. So 2 exercise. So obviously, if radical I is irrelevant maximal ideal or one belongs to it, then it is empty. Z of Pni is empty, and if Z of Pni is empty, means what? Means if you look at a zero set of I in an plus 1, then it cannot contain any point other than origin, because if it contains some point P in the origin, then since I is a homogeneous ideal, it contains the whole line, any point different from origin, that is, then of course it contains the whole line containing origin and this point, and then this P, this P as a projective point will lie in the zero set of I, which will contradict the assumption that zero set of I is empty. So that tells you that if zero set of I is empty, then zero set of I as in the projective set is empty. That tells you that the zero set of I as in an plus 1 has to be either a point or either the origin or the empty set. If it is empty set, then one belongs. Then of course one has to belong to I by Hilbert Nullstellensatz. If it is a point, that then if it's the origin, then we know that its radical is the irrelevant and then radical of I is the ideal of definition of the origin, which is x0 to xn. Okay, so maybe I've told you what the verbally what the proof is. You can write it down. Okay. Any questions? Okay, so maybe we'll finally. So I wanted to give you a bijection between maximal homogeneous, which we define homogeneous maximal ideal, and points of Pn. Yeah. So let me do that bijection, and then that will be the end of today's class. Yeah. So maybe I can write it here. Maybe I'll write it here so that the definition is handy, and I hope it can be done in this page itself. Okay, so let's call it Hilbert Nullstellensatz. So this is also Hilbert Nullstellensatz because it's sort of correspondence between points and certain maximal ideals of this polynomial. So let K be an algebraically closed field. So remember that bijection holds only for algebraically closed field, points of affine n space and maximal ideal of kx naught to xn. So here also we need that K be an algebraically closed field. What happened? M contained in kx naught to xn homogeneous ideal. homogeneous ideal. M is homogeneous maximal. Homogeneous maximal. That means maximal among homogeneous ideals whose radical is properly contained in x naught to xn, if and only if there exists P in Pn such that M equals ideal of definition of P. Yeah. So what is the proof? So maybe the two directions. So of course, if P is of this form, is a point in so if P is this thing, then we want to show that ideal is a ideal of definition is a homogeneous maximal ideal. A0, A1, AN. Then we know that I of P. So this calculation we did is same as A naught x1 A naught x1 minus A1 x naught to A naught xn minus in An x naught. Yeah. And so ideal of definition of P is this. So we only have to show that this is maximal among the homogeneous ideal properly containing this. Well, so we know that this is a prime ideal, yeah, and so we know that we in fact showed that IP is a prime ideal. Of K x naught to xn, and what is the zero set of IP in the affine n plus 1 space? What is this?
It's a line, right?
Yeah, it's the line connecting A0 to AN with origin. Yeah, so this is line joining A0 to AN and the origin. Yeah. Right. So now, if J is some homogeneous ideal which properly contains IP, then we want to show that it has to be. So we are trying to prove that it's homogeneous maximal. Yeah. So we have to show that if J is a homogeneous ideal which properly contains this, then its radical is x naught to xn, or or bigger. Yeah, it could be the whole ring as well. So so let J properly contains IP. Yeah, and J homogeneous. And J homogeneous. Yeah. So if we have such a J, then what do we know about V of Z of J? Z in the affine space, let's say. Yeah. So Z of J is going to be contained in this line. Yeah, Z of J is contained in this. Maybe we'll call this line L. Yeah, so that it's convenient, equals say LC. Yeah, and this line L in AN plus 1. So Z of J is a proper subset of L. Yeah, it can't be equal to L because we are taking strictly bigger, and IP is a prime ideal. You are taking something strictly bigger. Yeah, so it's going to give you you are going to get a proper subset. Yeah, and so it's properly contained in L, and Z of AN plus 1, since J is homogeneous, Z of AN plus 1 of J is a cone. Yeah. But that's not possible, right? That means this has to be the zero. This has to be the only possible, because if it contains any other point of the line other than 0, then it will contain the whole line. Yeah. But since J is properly contains IP, ZAN plus 1J is contained in L properly. Yeah. The radical of J is strictly bigger than IP. Yeah. So there is a among radicals there is an inclusion reversing bijection. So that tells you that so if Z of J AN plus 1 is 0, that tells you that radical of J is ideal of Z of AN plus 1. So these are all in the affine setup. Yeah, I'm not really using it. And this, of course, is this is 0. So ideal of this is just x0 to xn. Okay. So that tells us that hence IP. So any homogeneous ideal which is strictly bigger than this, bigger than IP, its radical must be equal to the relevant maximal ideal. So hence IP is homogeneous maximal. So we have proved one direction. Yeah, and I guess this direction doesn't require Hilbert Nullstellensatz like in the other setup. Yeah. Now for the other directions, so let M be homogeneous max. Is it maximal homogeneous or homogeneous maximal? Yeah. So it's just homogeneous maximal. In K x0 to xn, we want to show that M is I of P for some P. Yeah. So what do we know? Homogeneous maximal means, of course, is homogeneous and it's so it's contained in x0 to xn, and radical of M is properly contained in x0 to xn. Yeah, it's not can't be equal to this, right? Okay. So by Hilbert Nullstellensatz, what we get is that V Z 0 set of M in AN plus 1 is it contains the origin because this is there, and since radical of M is properly contained in this, it contains origin, and it contains origin strictly. So there is something more than origin in there. Yeah. So maybe. Yeah. So so if it was equal to origin, then by Hilbert Nullstellensatz, radical of M is going to be. Yeah. So here that's why Hilbert Nullstellensatz is here. Yeah. So equality would imply radical M by Hilbert Nullstellensatz will imply radical M is x naught to xm. Yeah. So it strictly contains this. So now you just take some point, and then that will be the so point on. So let P be an element of, or maybe let's call it A be an element of non-zero. Yeah. Then of course A0 to AN, this belongs to sorry, this yeah, so this belongs to Z Pn of M. Yeah. Which implies by this contravariant thing that I of this point ideal of this is contains M. Yeah. This belongs to the zero set of M. That means M is contained in the ideal of definition of this thing, which implies M has to be equal to, because M is maximal and this is homogeneous maximal, so M has to be equal to P. M is homogeneous maximum. So it and this guy left hand side is a homogeneous guy whose radical is properly contained. Okay, so that completes the proof of this version of homogeneous version of Hilbert Nullstellensatz. So points in projective n space corresponds to maximal ideals of this kind. A homogeneous maximal of this kind. Okay. Any questions? Okay, so maybe this is a good place to stop.